Welcome back to this Chapter 2 AS Chemistry lecture series. We're now going to do Section 3, which we're going to look at the subshells and the atomic orbitals. So we already discussed the energy levels and the numerical values that we associate to the energy associated with those energy levels. We're now going to look at the subdivisions of those energy levels. So how are those energy levels, which essentially are just regions as we move up away from the nucleus, how are those subdivided? So energy levels are subdivided into what we call quantum subshells, or for short, just subshells. Subshells are regions of principal quantum shells where electrons exist in defined areas associated with a particular amount of energy. Now, that's the official definition, and it can be kind of worthy. But subshells are essentially just subdivisions of shells or subdivisions of levels. Now, because of that, we can also sometimes call them sublevels, which is my preferred name. But sublevels, subshells, they mean the same thing. Essentially, each energy level can be subdivided into sub-levels or subshells. The subshells are going to be distinguished by 4 unique letters, either S, P, D, or F. Those letters correspond to the shape that those levels take. So the letters S, P, D, and F are going to correspond to the shape of the sub-levels, because sub-levels are essentially just groupings of areas with the same shape. As you can see here, each energy level is subdivided by different amounts. Even though there are 3 or 4 different types of sublevels, S, P, D, and F, not every energy level has all of them. For example, energy level 1 only has the S subdivision. So energy level 1 is just one big S subshell or sublevel. Energy level 2 is subdivided into 2 different ones, S and P. Energy level 3 is subdivided into S, P, and D. And then energy level 4 is subdivided into S, P, D, and F, which is not shown here because technically speaking, F only shows up in elements with more than 57 electrons, which are not very common on the AS exam. So we're mostly going to be focusing on S, P, and D, although F, you should know F exists, but not much more than that. So the energy level sublevels are arranged in increasing energy, S, P, D, and F. But you have to be careful with that. Why? When we say that the S sublevel has less energy than the P sublevel, which has less energy than the D sublevel, we are referring to the S, P, and D sublevels within the same energy level. So for example, if we look here, the S sublevel, let me change colors. The S sublevel in the third energy level, we call that 3S, third energy level, S sublevel, has less energy than the P sublevel in the third energy level, so 3P, and that has less energy than the D sublevel in the third energy level, or 3D. However, the 4P sublevel, we have it up here, has more energy than the 3D sublevel. Even though it's a P sublevel, it has more energy than a D sublevel in a lower energy level. So when we say that the S sublevel is lower in energy than the P, which is lower in energy than the D, we are referring within the same energy level. Once we go over to a different energy level, that changes because the P sublevel in fourth energy level is higher in energy than the P sublevel in the third energy level, so on and so forth. So you gotta be very careful. You can only compare those sublevels in the sense of within the same energy level. And we did study this last year in honors chemistry to some extent. Each subshell can only hold a specific number of electrons. And this is kind of where the idea that each energy level can only hold this specific number of electrons comes from. The S sublevels can only hold 2 electrons. The p sublevels can hold 6 electrons in total. The d sublevel can hold 10 electrons, and the f sublevel can hold 14 electrons. Again, we're not going to talk much about the f sublevel, but we should know that it can hold 14 electrons. The order of the subshells in terms of energy does not follow the regular pattern. Now, you got to remember, this is what we just talked about. Just because it's an S sublevel, it does not necessarily mean that it will have less energy than a P sublevel if that P sublevel is in a lower energy level. So if we look at this right here, we can see that as we move up, those energy levels and their subdivisions start to overlap. The first energy level has an S sublevel, and that's why it can only hold 2 electrons. And let's write that down here. And that S sublevel is really the lowest out of the low of any sublevel. The second energy level can hold 8 electrons because the P sublevel can hold 6 and the S sublevel can hold 2. So in total, that's 8. And both of those follow the order that you would expect. S is lower than P, and both of those are higher than the 1s sublevel. It's once we get to 3 that things start getting tricky. The S sublevel can hold a total of 18 electrons because the D sublevel can hold 10, the P sublevel can hold 6, and the S can hold 2. Now notice, it's the order you would expect, S, P, D, within the third energy level. But if we bring the fourth energy level into this, you'll notice something very interesting happen right here. The fourth and third energy level actually overlap. The 4s, which is the lowest sublevel in the fourth energy level, is lower in energy than the 3d sublevel, which is the highest energy level in the third energy. Sorry, the highest sublevel in the third energy level. So what happens here? That means that the order of the sublevels is not what you would expect. Because if you ask most people and you explain this to them, they would expect the order to be 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, 5s. They would expect them to go SPDF in order from first energy level all the way up to the highest energy level. However, the actual order of these sublevels, and I'm going to write the beginning of it right here in the bottom, is let me make that a little bigger. 1s, then 2s, then 2p, then 3s, then 3p, and up to there is what we expect. But after 3p, the next one up is not 3d. It's actually 4s. And the reason why it's 4s is because the 4s sublevel is technically lower in energy, as we can see in this overlap, than the 3d. Then the 3d comes in. So that pattern is actually interrupted by that 4s sublevel. Then it starts kind of go back to normal. You get the 4p. And then you don't get the 4d. You get the 5s. And then the 4d. Because again, if you notice right here, the pattern is yet again interrupted. And there is an overlap between the 4d and 5s sublevels. The very top of the fourth energy level overlaps with the very bottom of the fifth energy level. And that means that the order of the energy levels is not what we expect. And we learned about this last year. We just didn't learn why. We just learned that the order was a certain way. And you learned a shortcut, which I'll show you again in this video, of how to figure out the order. Before we keep talking about the order, though, let's talk about how many electrons and which sublevels are in each energy level. Let me move on to the next slide. Let's get rid of all of this. So this is a chart, and you saw this chart last year, of how many sublevels are in each energy level and how many electrons they can each have. Each sublevel contains one or more atomic orbitals, which are the subdivision for the energy sublevels. So what is an atomic orbital? An atomic orbital is the region of space outside the nucleus that can be occupied by a maximum of 2 electrons. So essentially, orbitals are what sublevels are subdivided by. And they're specific shapes in space. And we group all of these shapes into groups that are similar, and we call those sublevels. Each specific kind of subshell, S, P, D, and F, has a specific number of orbitals and therefore a specific number of max electrons. So let's look at that, and then we'll look at all the specific shapes. The S sublevel can have one orbital, and because every orbital can have a maximum of 2 electrons, doesn't matter what kind of orbital it is, the S sublevel can have 2 electrons because it has one orbital. The P sublevel has 3 orbitals and therefore a maximum of 6 electrons. The D sublevel has 5 orbitals and therefore a maximum of 10 electrons. And the F sublevel has 7 orbitals and therefore a maximum of 14 electrons. So we can put all of this information together, the energy levels, the sublevels, and the orbitals. We said, let's go from the bottom up, we said that every orbital, regardless of its type, can have 2 electrons. So one orbital can have a maximum of 2 electrons. The S sublevel, we said, has 1 orbital. So the S sublevel, which only has 1 orbital, can have 2 electrons. On the other hand, if we have a P sublevel, the P sublevel has 3 orbitals, and therefore those 3 orbitals can have 6 electrons in total. The D sublevel has can have 5 orbitals, and therefore since each of those 5 orbitals can hold 2 electrons, there's 10 orbitals in total. And finally, the F sublevel can hold 7 or has 7 orbitals, and therefore those 7 orbitals, 2 electrons each, can hold a maximum of 14 electrons. Once we bring in the energy levels, that's where it gets interesting, because not every energy level has all of the sublevels. The first energy level only has the S sublevel, and every energy level after that has an S sublevel. The second energy level is where the P sublevel starts, and therefore every energy level beyond that has a P sublevel. The third energy level is where the V subshell, because remember subshell and sublevel are the same thing. The third energy level is where the V subshell starts, and therefore the V and the third and the fourth and every energy level beyond that have it. And the fourth energy level is where the F sublevel starts. And every energy level past that, 5, 6, 7, all have S, P, D, and F sublevels. Because of this, we get into a lot of different questions that can be asked on the Cambridge exam about this. Because we can figure out a lot of different things. We could be asked which sublevels or subshells are in a specific energy level. We could be asked how many orbitals are in a specific sublevel. So D has 5 orbitals, F has 7, P has 3, S has 1. We could be asked how many electrons are in an orbital, and the answer to that question is always 2. Whether it's an S orbital, a P orbital, a D orbital, or an F orbital, it can only ever have 2 electrons. However, we could also be asked for totals, right? How many total orbitals are in the second energy level? Well, if the second energy level has an S and a P sublevel, the S can only have 1 orbital, the P has 3, so it's a total of 4 orbitals in the second energy level. We could also be asked how many electrons. Since the fourth energy level, for example, has S, P, D, and F, that is 1 plus 3 plus 5 plus 7 is 16 total orbitals in the fourth energy level. Well, if there are 16 total orbitals in the fourth energy level, and that energy level can hold, or each orbital, can hold 2 electrons, that means there's a total of 32 maximum electrons in the fourth energy level. We could also be asked how many electrons in a sublevel. So the D sublevel has 5 orbitals, therefore it can have 10 electrons maximum. So you can see how we can be asked almost any number within this chart on the AICE exam. The idea here, and I want to make a very strict point here, is don't memorize this chart. What you want to memorize is how many sublevels are in each energy level and how many orbitals in each sublevel. From there, you should be able to figure out through logic and critical thinking any question they ask you. If you memorize this chart, it's actually going to take you longer to answer questions because then you'll have to remember the chart, maybe draw it out, look for the number you're looking for, and then answer the question. Whereas if you know which sublevels are found in each energy level and how many orbitals each of those sublevel has, and the fact that you can only have 2 electrons per orbital, then you can just answer those questions much more naturally in one straight line of critical thinking. Again, this level of chemistry is not about memorization, it's about understanding and application and using your critical thinking. Now, we talked about the shapes of the orbitals, so let's talk about that, or we mentioned the shape of the orbitals earlier. Let's talk about that a little more. Atomic orbitals are regions in space with specific shapes depending on their type. So we said that there are 3 p orbitals, for example, in the p sublevel. Well, why are they p orbitals? They're p orbitals because they all have the same shape, and they're grouped within the same sublevel. Orbitals of the same type are always going to have the same shape. It doesn't matter what energy level they're in. The energy level changes their size, not their shape. If it's a p orbital, it's always going to be, in this case, a dumbbell. We'll get into this in a second. But it's always going to be the same shape. The size is what's going to change from energy level to energy level. Also, what distinguishes one p orbital from another within the 3 is their orientation. Whether it's up and down, side to side, back and forth. The shape of the s and p orbitals can be seen below or on the PowerPoint, and there can be assessed in the AS chemistry exam. So, for example, you could be asked to draw an s orbital or to draw a p orbital. What you will not be asked to do, however, is to draw F and D orbitals because their shapes are much more complex. An s orbital is always going to be a sphere, so we draw it as a circle on the AS exam on paper. The p orbitals are what we call dumbbell shapes, and we draw them like this infinity symbol. Now, there are 3 different p orbitals: px, py, and bz. The difference between px, py, and bz is not their shape. As you can tell, they're all this infinity dumbbells shape, but their orientation. Px goes back and forth, away and towards you. Py goes side to side, and pz goes up and down. And that's because they're named after the axes they're on. Px is on the x-axis, py is on the y-axis, and bz is on the z-axis. This is, of course, in a 3-dimensional axis. Now, how do we place electrons in that order that we saw earlier? Electrons are always going to fill orbitals according to the off-ball principle from lowest in energy to highest in energy. Now, this does not mean energy level, and that's a very big misconception. This does not mean that electrons are going to be filled energy level 1 first, then energy level 2, then energy level 3, 4, 5, 6, 7, 8. This means that the electrons are going to be placed in the lowest energy orbitals. As we saw earlier, those sublevels are going to overlap over different energy levels. So the 4s is actually lower in energy than the 3d. The 5s is actually lower in energy than the 4d, even though it's in a higher energy level. The order depends on this. Now, you could memorize this. Memorize that the 4s comes before 3d, the fact that 4s comes before 4d, but after 4p. But that's a lot of memorization. Again, that's not the point. We can use a shortcut, a visualization shortcut, in order to remember this. Essentially, what we're going to do is we're going to draw the sublevels into columns. So S first, then P, then D, then F. And then the energy levels are going to be rows. So we have 1S, because that's the only sublevel in 1. 2S and 2P, because those are the only sublevels in 2. 3S, 3P, 3D. 4S, 4P, 4D, 4F. And then everything else from there is F, up to F, and so on and so forth. And then we're going to cross them out diagonally. So when I go through one diagonally, then go back to the next diagonal, cross them out, back to the next diagonal, cross them out. And this is what's going to give us the order of the sublevels. So if I follow this, and obviously you're not going to do this for every single one, you do them for the ones that you need. But if I follow this, 1s is the first orbital or sublevel that's filled. Then we finish the diagonal, we go to the next diagonal. The next diagonal is 2s. Then we keep going and we finish that diagonal. We go to the next one, we go through 2p, then 3s. Then finish that diagonal down to the next one. So if we follow the arrow, then 3p is next to be filled. Then 4s is after that. Finish that diagonal, follow the arrow. So then after 4s, 3d. So notice, we go from a larger energy level to a lower one. And then after 3d, we go back to 4p. And then we keep going up, 5s, before we drop yet again from 5s to 4d. Then 5p, 6s, 4f, 5d, 6p, 7s, then all the way from 7s all the way up to 5f, 6d, 7p, 8s. So this is the order in which the sublevels are filled with electrons. 1s is filled first, then 2s, 2p, 3s. So if we need to do electron configurations, which we'll talk about in a little bit, we will do so in this order. Again, you could memorize this, but that's not the point of chemistry, because you're gonna have to memorize a lot of things. Might as well save space in your brain where you can. You can just draw this diagram whenever you need it, and then use it to figure out the order. So if we had, let's say, 10 electrons, then those 10 electrons will fill from lower to higher. So if we had 10, the s sublevel can only hold 2 electrons. So that's 2. Oops, let me make this a little smaller. So that's 2 electrons in s, into 1s. 2 electrons in 2s, because that's the maximum this can hold. Then that's 4 plus 6 electrons in 2p. That's 10 electrons in total. If we had 15 electrons, then we would just keep going. That's 10 plus 2 that can fit into this 2s. 3s is 12. And then if we need 15, we need 3 more. So even though 3p can hold 6, we only need 3 more electrons. But we'll talk more about this once we get to electron configuration. Now, there is a shortcut that you can use in order to memorize this that includes the periodic table. So if you look at this is actually the periodic table. Let me bring that up. So this is actually the periodic table. You can see the 2 columns right here, the transition metals, the 6 columns at the end, and the 2 in the bottom. These are what we know as the S block, are the first 2 columns, including helium over here in the top left, right? The D block are the transition metals, which are the 10 columns in the middle. The P block is the 6 columns at the end, excluding helium. And the F block is those 2 columns in the bottom. Let's say we wanted to know what order we should follow to do the electron configuration of titanium. Titanium is right here. So let me write titanium in. So titanium is right here. So we wanted to know what the electron configuration of titanium is. We wanted to know where to put electrons when we're trying to do the electron configuration of titanium. Well, in order to do that, all we have to remember is that for doing electron configuration, for figuring out how many electrons go into the specific orbitals and sublevels, the period on the periodic table is related to the energy level. So I'll put E level here. For S and P, the period is the energy level. For D, the period minus 1 is the energy level. And for F, the period minus 2 is the energy level. Because notice, here, third period, that's 3s right here. For this, 1, 2, third period, that's 3p. But for the 1, 2, 3, this is the fourth period, but this row all have 3d. And that's because of the order that we discussed before. The fact that the d sublevel comes in 1 before. For the F, again, same thing, because the F, this right here is actually the 6th period. Let me put it in a different color. This is actually the 6th period, and this is actually the 7th period. So 6 minus 2, this all have 4 as their sublevel. As their energy level, sorry. And then 7 minus 2 is 5. These are all 5F on the F block. The block itself refers to which sublevel they're in. So all of these elements end in the sublevels. All of these end in S sublevels for electron configuration, so on and so forth. So if we want to do titanium, all we have to do is go through these and say, okay, if we have titanium here, then let's do it up here. We go through, if we go from the beginning, we go through 1s. Again, this is the S block and first period. So it's 1s. And we go through 2 of the, actually, we'll do that later when we're looking at electron configuration. But it's 1s. So there's going to be electrons in 1s. There's already electrons in, then after that is second period, S block, so 2s. Then it's second period, P block, so 2p. Then third period, S block, so then it's we have 3s. Third period, P block, so we have 3p. Fourth period, S block that we got through, so that's 4s, sorry. And then titanium is the second element in the fourth period, D block. So because it's the fourth period, but it's in the D block, it's not 4D, it's 3D. And there's going to be elements in there, electrons in there. But it's only going to be 2 electrons. So 1s, 2s, 2p, 3s, 3p, 4s, 3d. And that is the order in which the sub-levels of titanium will be filled by using the periodic table. And just remembering that if you're doing S or P block, the period is the energy level number. If you're doing the D block, it's a period minus 1. And then the F block, which again will not show up on the AICE exam, but it's a period minus 2. And then that will give you the order by using, instead of that other chart that we saw earlier, by using the periodic table. You can use either one. There's no wrong answer. And that will give you the order the sublevels have to be filled into the periodic table, into the energy levels. All right. That is it for this section. I'll see you all next time for section 4.